So, as promised, here are the physics momentum problems, evens. So, here is problem number 2. A 3-kilogram ball is accelerated from rest to a speed of 10 meters per second. I'll actually come back to that in a second. Let's talk briefly about what we're dealing with here. We have impulse, which is just when I apply a force over a certain amount of time, is equal to the change in momentum, which is the mass times the final velocity, it's a v, minus the mass times the initial velocity. And that's just the change in momentum. It started with a certain mv, it ended up with a different mv, it changed. We had to apply a force over a certain amount of time to cause that change in momentum. So we might be working on one side of the equation, we might be working on the other. We have to be prepared for that. So again, number 2, we have a 3-kilogram ball moving at 10 meters per second. Well, that means we're working on this side of the equation. How did it get there? What's going on? I don't know, but let's calculate the momentum. So momentum, P, is 3 kilograms times 10 meters per second, also known as 30 kilogram meters per second. That's momentum. That's A. Now B, what's the impulse? Well, like I said, it's the same. The impulse to get it, if it was started at rest, if this part of the equation was 0, because there was no velocity, which it often is, the impulse would have to equal 30 kilograms meters per second, because the impulse over here is equal to the change in momentum. That's momentum, that's the impulse. And finally, C says, all right, well, if we give it a constant 40 Newton force, how long does the force act? All right, so force times time equals momentum. Actually, we call it change, but we can just use momentum for now. We know that the force is 40 newtons. We don't know the time. We know the momentum's 30 kilogram meters per second. Divide both sides by 40 newtons. And the time is 0.75 seconds. How do I know it's seconds with all this mess? Well, if you keep everything in kilograms, meters, newtons, and seconds, time is always going to be in seconds. That's number 2. Let's go to number 4. A 60 kilogram high jumper lands on a mat after her jump. And that brings her a stop after 1 second. So she had a bunch of energy when she jumped, and it got impulsed into the mat. She was traveling at 5 meters per second when she landed on the mat. So the speed at the top was 0 meters per second. What is the change in momentum for the jumper? So we're looking for all these pieces of information again. We know that the initial speed was 0, so all of this will vanish. And now we say, okay, they gave us time equals 1 second to stop her. Her speed was 5 meters per second right before she hit the mat. That's V, not M. And her mass is 60 kilograms. So we don't know the force. Got to work on this side of the equation over here. So momentum is 60 kilograms times 5 meters per second. Momentum equals 300 kilogram meters per second. That's A. What is the force felt by the jumper upon impact with the mat? Now the mat does a kind of reverse impulse, so I suppose we could give this a negative, but we don't need to. But it's, again, we don't know the force. We know it took 1 second. and we know it had to take away 300 kilogram meters per second of momentum. So we divide both sides by 1, which we really didn't need to do. And we get force is equal to 300 newtons. Don't like my zeros. There we go. That's it. Number 6. A baseball player hits a .155 kilogram fastball. You know what? I don't trust myself, so let's start writing these down. 0.155 kilogram. Traveling at 44 meters per second. V equals 44 meters per second. I bet we're going to have to find the momentum with those two. So I'm not going to do the math, but I'm just going to start setting it up. Even though I have no idea what's going on with this problem. No, I haven't looked at it in advance. I'll come back to that in a sec. Because I know I got speed and I got velocity. Sounds like I need momentum. He hits it into center field at a speed of 50 meters per second. If the impact lasts .00450, what was the force that he hit the baseball with? So this is the V initial. This is the initial momentum. 44 times .155. And then the V final is 50 meters per second. But it's in the other direction, so one of these is going to have to be negative. We're going to have to add these two together, not subtract them. And the mass is still 0.155 kilograms. So the P final is 0.155 kilograms times 50 meters per second. So it went from 44 going this way to 50 going that way. So we got to add them together because that's how much of an impulse we had to put on there. The P final is 7.75 kilograms meters per second. I'm going to make this one negative. I'm going to assume that it's coming at us, so we call that negative, and positive would be going away from us. So negative, negative, so we'll say that's negative. Now I've got an impulse for 0.00450 seconds. So we know that F times 0.00450 seconds equals 7. Now I'll write it out first. The final momentum minus the initial momentum, 7.75 kilogram meters per second, minus negative 6.82 kilogram meters per second. Negative, negative is a plus. So we know that force times 0.00450 seconds equals 14.57 kilogram meters per second. Divide both sides. I'm going to get a sizable number here. And the force is equal to wow, 3237.8 newtons. Let's round that to 3,200 newtons. So, got to put a lot of force on that ball. Number 8. Tricky problems. In terms of impulse, why is a ride much more comfortable when an airplane is flying at constant speed versus when it's taking off or landing? So constant speed. We know that the net force equals 0. Takeoff or landing, we're accelerating or decelerating. Therefore, we feel a force, which is a lot less comfortable than just flying along nice and steady. Number 10. And we'll move it to the next page. If identical bullets are shot from a pistol and a rifle, a bullet shot from a rifle will travel at a higher speed than a bullet from the pistol. Why? Hint, assume shooting force is the same in each case. The barrel is longer in a rifle than the barrel of a pistol. My guess, and I really don't know, if you shoot out of a pistol barrel, and I'm not trying to draw a gun, just the pistol, the way it works is that there's a little mini explosion here, and it forces the bullet out. While the bullet is stuck inside this tube, all the gases from the explosion push it out. But they only push it out while it's in the tube. Once it gets out of the tube, these gases get to just kind of fly all over the place, and they no longer are pushing that bullet. Whereas the explosion in a rifle barrel has a lot longer to push before the bullet gets out and the gases all escape. So the rifle has F times T. That will, let's just assume it's the same, although rifles usually have bigger bullets, so they'll have a bigger force, but T is definitely bigger in a rifle. And I also do know that the longer a rifle barrel is, up to a point, the more accurate it is. So, last but not least, number 12. Show that the relationship between impulse and the change in momentum is another way of stating Newton's second law of motion. Interesting. No idea how I'm going to do this. I do know that the second law is A equals F over M. I know that I can change that by multiplying both sides by M to get F equals MA. And it said impulse and change in momentum. So F on this side, we'd have to multiply by T. We'd have to multiply the other side by T. And all I can do is with the units now. That's an impulse. Masses in the equation, F dot T equals M times V final minus M times V initial. So the mass is still here. And A times T, if we just do the units, meters per second squared times second, we'd cancel the S, and we'd get meters per second, so it equals velocity. So you could look at it from that way. Change in velocity is going to be just like an impulse change. I wouldn't worry about that one too much, but it is kind of interesting to see how everything ties